It's 11:10, so we can get started. And also the room is full. So I'm extremely happy to introduce our CQIQC seminar speaker today, Alexei Bylinskii. Alexei is actually a U of T alum. He did engineering science, I guess, many years ago now. And we also overlapped in graduate school, and we spent a few years working together at QuEra, where Alexei is actually employee number one. So he has seen the company go from Alexei at a desk to quite a large organization now. So if you have questions about that kind of thing, I'm sure he would be happy to share some of his experiences. But today he'll be telling us about some of the science that the company has been doing. So take it away.
Thank you. Mic is working? Okay. Oh, good. All right. So today I'll talk about science that we did with some of our programmable quantum computers at QuEra with collaborators. And one thing I want to emphasize before I even start is that that's an opportunity that you also have. Our machines we strive to make available to the world to play with, because we would really like to leverage the ideas and the creativity of the world to demonstrate the usefulness and the next steps for our platforms. But by show of hands, is there what's the mix of experimentalists and theorists here? Theorists, yeah. Theorists, experiment. Oh, good, even split. Anybody working on QEC? Oh, that's 1.5. Anybody building software for quantum in some way or form? Okay. Applications of quantum. Okay. So a lot of theory that's not necessarily quantum information, I guess. Okay. Good. Okay. So I think I'll have some introductory slides about that. But the main idea is to explain to you two different systems that QuEra builds, and give you kind of examples of prototypical scientific work that can be done with these systems. And the way we think about our machines is they are platforms for science and development of quantum computing itself. They're not yet bringing business value at a scale that people are aiming for. But this is a real market. There's a real market for researchers using these machines, and we're engaging with many of them across the ecosystem. And these are products of just two of those engagements. So the first machine is actually the machine that we've had available online to the public for the last 3 years. It's an analog quantum computer where you're actually programming the Rydberg Hamiltonian directly. It's called Aquila. And the second machine is where you program the quantum circuit or the level of gates. And that's actually the programming model that you might be familiar with from other systems, IBM and others that are available. And in this system, I will dive into this scientific result of observing string breaking in a 2+1D lattice gauge theory that was implemented in this Hamiltonian. And in this system, I will dive into the first demonstration of logical magic state distillation. And magic states are these critical resources for making fault-tolerant quantum computers also universal. Before I dive into these systems and to these projects, I will do the obligatory intro to QuEra. And for those of you who have other questions about QuEra, we can discuss later as well. So our mission is to accelerate innovation by building useful, fault-tolerant, scalable quantum computers. And there's a progression of technology that we're trying to follow towards that. As I mentioned before, our first generation machine that's been available for a while now is an analog Hamiltonian programming machine. No error correction. It's noisy. It takes effort to figure out what it actually is good for given that noise, right? Similar story for our first gate-based machine, except that now it is really this universal programmable model. It's a universal quantum computer, still noisy, still fault tolerant, still not fault tolerant, but it is a platform where you can play around with fault tolerance constructs and start to do some early quantum error correction on that machine. And then the next generation of machines we're building at QuEra actually will be logical qubit machines where you would be defining logical circuits and it would be error correction under the hood, and the computation can run continuously without losing its information. So these are our core technologies. We are a full stack company, so besides the core of the machine, we also develop software that make these machines usable by researchers, by customers. In the context of the first generation machine, we developed very basic constructs like APIs, software development kits, simulators, and we did the integration with the cloud. In the context of our first gate-based machine, we're now in the process of developing compilers, different levels of abstraction at which people can interface with the machines. We're working on HPC integration. I mean, that's one reason I was asking about anybody working on software, because that's a big part of what we're doing nowadays. And then, of course, for products and services, Aquila is that machine that's been available. It's been available on Amazon Braket as a cloud service, and the model of programming is analog Hamiltonian simulation. In the context of Gemini, it's actually our first machine that we installed on-prem at a customer site. We shipped it to Japan, to the institute, effectively what is Japan's National Institute of Standards and Technology. It is there now. We are kind of bringing it up and hoping to launch it next year. In the context of that machine, we also will have a bunch of engagements where we co-design the architecture, and which is soft configurable in our system, and the algorithms, so that we can really demonstrate the biggest impact for these early demonstrations which suffer from noise. And then the next generations of machines, we really hope will become this kind of just touching this boundary of utility, where you're programming logical circuits and you can start thinking about business solutions and having these machines as OEM devices that really are integrated into some kind of HPC fabric without the user having to think about whether the machine is quantum or classical. That's one day, but it's not there yet. As I mentioned before, we engage across the ecosystem with institutions that want to invest strategically into quantum, academic institutions. In the case of yes, the DoD and DOE labs. We do have this kind of QuEra Quantum Alliance, which brings in partners that we are working with on different parts of the stack, all the way from kind of low-level controls through applications. We are engaged in national quantum ecosystems in Japan and the UK. Our kind of lead investor from Series B is actually a developer of quantum computers themselves, Google Quantum AI team. We recently got phase 2 of the DARPA's Quantum Benchmark Initiative, working with NVIDIA to figure out how to decode these large-scale fault-tolerant computers, and so on and so forth. So there's a lot of these strategic kind of either investors or customers or partners. But at the end of the day, all the users of our machines and our technology are at some level academics. They're all researchers. They might be working for different institutions, but they're all playing with this technology to see where the future will be, and how to help us get there. And so I invite everybody to think of ways that this can be useful to you, or how we can work together. So Aquila, this first generation machine, it's kind of our flagship product these days. It's been online on the cloud for the last 3 years. Actually, it was recently its anniversary. And the service that you can access it through is called Amazon Braket. It's one of AWS's Amazon Web Services services. And it's available there for 130 hours a week. It is actually more time than is used in reality. So, that's all good news for you if you want to go up and use it, because you more or less have live interaction with the machine. But it is a queued system. So if there's people up front, then you have to wait for a batch job to be executed. HPC style batch job execution. It's in its best months, it gets up to 99% uptime, which is kind of record for these kinds of optical setups that are finicky in many different ways. In the last 3 years, there's been quite a lot of activity from scientists doing proof of concept demonstrations or scientific studies on the machine. So there's 39 papers that I counted that have Aquila data as kind of the core of the paper, with 34 of those users accessing the device through Braket, through this cloud service where it just runs on its own. 28 of those papers were without any QuEra assistance or QuEra co-authors, which basically means, okay, this machine, this technology is mature enough that people can really wrap their head around it and use it on their own. I mean, again, they're all still researchers, but we who build the machine don't necessarily need to guide them through it. This gate-based machine is at an earlier stage. So for the next year or two, we will be very closely engaging with everybody who's trying to use it, as we also trying to mature it to the level where Aquila is today. It is our first on-prem installation. It is sitting right now next to this GPU supercomputer at AIST in the suburb of Tokyo. I was there last 2 weeks, actually. I just got back. We're ramping up our operations there. The machine is not yet available, but we're hoping to launch it in 2026, first half of 2026. And the way to think about this machine, okay, it's his first gate-based machine, but really it could be used in many different ways. One of the key ways we're hoping to engage with users is on developing quantum error correction on top of it as a platform. And of course, like all the other machines out there, it is a NISQ device with physical qubits, 256 physical qubits. And this is where you can start to run early proof of concept things that maybe even use the HPC center as a kind of a hybrid workflow or hybrid algorithm. And then finally, we think it's a very, we're now working on APIs that would allow low-level access for the users, so signal-level access for those who want to build compilers for the neutral atom architecture. And we're collaborating with actually quite a few academics or compiler developers from the world of classical engineering. There's a lot to learn from on that front. So that's QuEra. Now, a brief intro into the neutral atom quantum computing technology itself. There's basically 4 ingredients for the technology I'm talking about. Of course, atomic physics is a big field, and people use all kinds of systems to leverage atoms in various, as quantum simulators, for example. But the systems I'm talking about are really, they use individual atoms trapped in optical tweezers, arrays of optical tweezers, and they use Rydberg blockade to create entanglement between the atoms. So for those of you who are not atomic physicists, all of this happens in vacuum. So your atoms start as a dilute gas, and then this then they get trapped at the focal point of these laser beams, and then get cooled, initialized to correct atomic state, and then you can start using the internal states of that atom as a qubit. And one of the internal states is this Rydberg state, which basically, when you drive a laser pulse to bring that atom to this Rydberg state, it's a big orbital, and it makes it interact with an atom in the vicinity. And the interaction is 1 over r to the 6, which basically means that if the atoms are a little bit far apart, they actually don't see each other. And if they get closer, only one of them can be excited at a time. They kind of blockade each other from being driven into this excited state by effectively the interaction energy shift of the atomic level. And so this kind of Rydberg interaction is both at the core of how Aquila, this analog machine, operates. This is this is the term in the Hamiltonian. You kind of program by positioning atoms. These xi's and xj's is what's programmable in Aquila. And it's also the basis for how the 2-qubit gates work in the gate-based architecture. The way to think about it, it's a CZ, it's a phase gate where if both atoms are in the ground state, or if only one of them is in the excited state, then a 2-pi pulse brings the atoms back without any phase accumulation. But if one of the atoms is in the Rydberg state, then the other atom is blockaded, and there's a pickup of minus sign on that. So it's a C-phase gate that's now becomes like your building block in the quantum circuit. So that's the basic idea. And I'm not going to go through all of the literature that has sprung up in this field in the last 8 years or so, but I'll tell you about kind of the key milestones that have driven QuEra's technology roadmap. And it all started with this 2017 paper from the group of Misha Lukin and Vladan Vuletic, where the first deterministic preparation of atoms and tweezers was achieved, where you could actually assemble these large arrays of atoms, individually imaged atoms, that you could control their interaction without having holes in there. And the way that was done is actually not by some kind of fundamental breakthrough, but just by engineering the system, where you can take an image of the atoms, see which tweezers are filled, and the ones that are not, you can feed back to the acousto-optic deflector to move your tweezers in such a way that refills and removes the entropy from the system. And that's kind of the basics of the platform. that everything else is based on. So this was like the first programmable Rydberg Hamiltonian. This was in 1D. And a few years later, the 2D version of that was demonstrated in a series of papers, actually. This is the first one. And soon after that, we actually put Aquila on the cloud with this 2D programmable Hamiltonian being the core model for programming it. So that's on the analog side. A year later, after we put the analog machine on the cloud, some of the first results were being shown on using the system as a gate-based architecture, starting with coherence-preserving transport of atoms and tweezers. Turns out, and by the way, trapped ions have been doing this for years, and that's one of the kind of key tenets for some of the platform's scalability for trapped ions. Turns out this works at a much larger scale for neutral atoms very, very well. And so what we can do now is, you can take a qubit, put it in the storage zone, pull it out of the storage zone, put it into the gate zone next to another atom. Any atom you choose, you have any-to-any connectivity to do your 2-qubit gates, you can put them back into storage. And now the architecture starts to resemble like the von Neumann architecture with different kind of, in the classical processor where you have, storage, processing zone, bus, information bus, and so on. And then, in parallel with this, the kind of record for neutral atoms, record fidelities were demonstrated with this Rydberg gate, around 99.5%. And then there was a very rapid progression of papers showing operating this gate-based architecture to a larger and larger scale. Quantum circuits and logical qubits, and more recently, actually last month, two very important papers came out of Misha's group showing all of the ingredients you need for fault tolerance in one system, and in a separate machine, showing that you could also push the scale to 3,000 qubits and beyond while operating the machine continuously. So with the atom system, you actually lose your qubits when you read them out at some rate. You have to replenish them. To really run a deep circuit, deep computation, you need to reload those qubits, and continuous operation was demonstrated in this paper. And I alluded to some of the next generation systems that QuEra is building today. They are that generation of machine which can operate continuously. All right. So let's go back to how Aquila and Gemini actually are built themselves. I'm not going to go into too much detail, but I do want to reveal the things that are important for somebody who's trying to use it. So the Aquila platform, okay, it's a programmable Rydberg Hamiltonian. Okay, here's the Hamiltonian. Here's the scheme of the rubidium-87 that we use. We just use these two states to encode the information in Aquila. That's the ground state. That's the Rydberg state. When atoms are in this state, that's when they interact and create this 1/6 potential for each other. It's a 2-photon transition between them. You can control the Rabi frequency, amplitude, phase, frequency of that drive. And that's what controls this term in the Hamiltonian. And this kind of detuning also goes into the excitation costs in this term of the Hamiltonian. So now you could also choose where your qubits will be. And actually the user programs the machine by asking for an array of coordinates, x, y values for each of the atoms that they want. So you can make it into a regular array. In this case, it's a Kagome lattice. Okay, it can be something arbitrary, whatever you want. So some people have used it to encode graph problems that they want to do an optimization on. In this case, that's more like a condensed matter quantum simulation problem, or something that looks more like an array of qubits in the quantum computer. So the positions of the qubits are programmable, and depending on where you put them relative to this blockade radius, the distance at which these qubits start to interact, you basically control the connectivity of this kind of pattern in terms of quantum interactions, but it's a local connectivity in this machine. Now, when we go to the gate-based machine, that will change. So now you have all of these, all of these parameters to program in terms of where the qubits are. That's how you typically encode the problem. You can control as a time series the amplitude, phase, and frequency of the drive between the ground and Rydberg state. You can control the detuning, and you also have an additional local degree of control where you can apply laser beams to the atoms you choose and shift their resonance, which effectively turns into this local degree of freedom of control for the detuning in the Hamiltonian. Yes?
Can I ask a few scale questions?
Yep.
The array there, how big physically is it?
Yeah, so the whole field of view that's available to use is 75 microns by 100 microns or so. And the distance, the typical distance at which you want your qubits, so this typical blockade radius is in the order of 6 micrometers. So if you're a little closer, they'll blockade. If they're a little further apart, they won't see each other. And you can choose what those spacings are.
And are the atoms placed one at a time?
How are they sorted? That's a good question. So what I'm not showing is there's actually more traps outside of the user programmable region. They're all loaded. They all start with like 60% or so filling fraction. You take an image and then you fill the user programmed pattern, to be what they asked for. And the way you do that is kind of like one row at a time. So in this case, this would be one step. You sort the entire row in one step. The next row sort the next step, and you can go through this whole thing in about maybe a few milliseconds. In this type of machine where you're kind of loading the qubits, pumping them, taking an image, sorting them, and then doing a very short quantum computation because of the coherence time is limiting you, and then starting over, the duty cycle of like actual quantum computation relative to all the setup and teardown is like 1 part per thousand. So mostly it's actually the shot rate in this machine is 3 per second. So every 300 milliseconds you start over. The sorting step is actually not the rate limiting factor in this case.
Your coherence time.
So the ground Rydberg coherence time, which is this manifold we're using here, is actually more like 5 microseconds. The gate-based machine works differently. So this is where you have your seconds coherence times between these hyperfine levels. And you store your information here most of the time, unless you want to do this very fast entangling gate. That's when you invoke the Rydberg state. And so in this case, indeed, the coherence time is seconds. And when you're making a circuit where you need to move qubits between the layers of the circuit so that you can create the connectivity you want to do the 2-qubit gates you want, each move costs you about 100 microseconds. So you can see that actually, if you have a really, really deep circuit, the kind of the operational clock of a machine like this is actually one of the downsides of this platform. Moving atoms takes longer than applying, gate pulses. Yes.
Sure. Some more really basic questions. You can go back to the last slide for a second. The N operators, those are occupations in
Of the Rydberg, yeah.
Right?
Mm-hmm.
So those are G operators. I could also think of as just raising and lowering operators, sigma plus and sigma minus.
That's right. Yeah.
And the Rydberg level is not trapped in the tweezer, am I wrong?
That's correct. So actually, when we do the evolution of this Hamiltonian in this model, you turn the traps off, and they don't have time to fly away before within this 5 microsecond coherence time and then you retrap them and you image them, and everything that was in the Rydberg state actually ends up being kicked out. So it's a destructive imaging, and the way you tell if it's ground or Rydberg is if you see the bright dot at the end, that was ground, and if you don't, then it was Rydberg. And there's some detection error that has to do with the atom either not being kicked out and falling back to the ground state, or being lost from the ground state on its own, and you think that it's Rydberg. And that's one of the things that dominates the detection errors.
And the ability to map that qubit onto a ground state qubit.
So in Aquila, you don't, but in the gate-based machines, that's where you actually mostly keep them in the hyperfine, and you only do a kind of almost a virtual pulse through the Rydberg state to pick up that phase and do the gate. Very good question. So there's some differences in terms of timescales for these two machines, and in terms of even this question about trapping. So for the gate-based machine, you're always trapping, and you actually when you do the gate, you very briefly turn off the trapping light and you recapture them.
Just looking at the pictures in the previous slide there, is there some sort of trade-off between how many qubits you can, or like how many atoms you can have in your field of view at a time versus how easy it is to move around. Because it seems like if there's more atoms, there might be less space to like route everything. Or is that not?
You mean for sorting them, or for the gate-based model where you're actually like shuttling them throughout the coherence of the?
Oh, I guess you're not sure.
Yeah. So in this one, you shuttle it. This one you shuttle them before you start the coherent evolution. So think of it as a preparation step. Whereas in this setup, you actually shuttling them while they're coherent, while the information is stored in the hyperfines. In this case, your geometry can be arbitrary, and depending on how arbitrary, there might be some limitations on how well this preparation step works in terms of filling the pattern you asked for. In this model, you actually have a regular grid of qubits in the storage zone and in the gate zone, and you have pretty well-defined lanes to shuttle your atoms through during the coherent evolution. So that's part of the design of this, is you have to make sure that you leave like corridors for moving the atoms through. You can kind of address any part of the storage zone that way. Make sense? Yeah. Well, so we transitioned to talking about the gate-based machine. Yeah, I mean, one of the things is the layout is fixed, but what the user programs is, your circuit, which has to be compiled now onto a set of layered operations where some layers will rearrange the atoms between the storage and the gate zone. Some layers will be applying a simultaneous 2-qubit gate. You might not be able to see this, but actually there's two sites here in each of these locations, which is set up for your 2-qubit gate. So you can put, an atom from here, take an atom from there, move them into this location so that they can be entangled. At the same time, you're moving another pair into this location. Once you fill the entanglement zone, you do a single coherent control pulse to do the 2-qubit gate, and all of the qubit pairs that you wanted entangled will be entangled in that one step. One of the things that is, difficult for the compiler problem is to assemble this array in the entanglement zone before you do your qubit operation. How serialized do your moves need to be? Do you go one at a time? Can you move blocks? I mean, it turns out we can move blocks of qubits while keeping them coherent, but there are some physical constraints on what moves are allowed, because we do that with these crossed AODs. So it's not a fully arbitrary control of your tweezers. It's a product space between X and Y. So you can move blocks. You can move rows, for example. You can move blocks of qubits, but you cannot move arbitrary patterns of qubits in one step. So you have to serialize that.
All movement in the same plane. You can't
Correct.
jump on.
For now, we are only working in one image plane. There are tricks, and people have shown them, where you can change focus. It's generally speaking, our belief is going full 3D doesn't make sense. Maybe working with two planes can give you some advantage. For example, for shuttling and packing things more densely. But that's a good question. We get that one a lot. It's like, why not go to 3D? The truth is, high-NA imaging is much trickier in 3D if you want to move between different image planes. Right. So the basic operations in this kind of, so here's your circuit. But one way that this circuit is different from an IBM type machine is you have this atom rearrangement layer. And one of the things I was talking about earlier is APIs. For our compiler developers, we would like to offer that control over the atom movement. For people who want to just think about the circuit in a way that's interoperable with all the other machines, our internal compiler has to decide what sequence of moves happens. Unfortunately, that does affect the ultimate error rate, the ultimate fidelity of the circuit. And we also have all kinds of simulation tools that allow you to kind of try to predict that. But that is something that we hope will become completely irrelevant once you have error correction. It's something, once you have error correction, basically, all of this noise would be taken care of under the hood, and you would have one metric to think about. How many logical qubits do I have? What error rate per operation do I get? That's where everybody wants to get to. It's not really there yet, meaning that to really write a good circuit, you have to think about the noises in this device. And that's something we tell all our users. It's like, okay, you know, the naive circuit that you might want to run will probably not work. Think about how to optimize it given the noises is pretty important.
Choice of going for much lower revert for Gemini than for Aquila?
We did go to my,
53?
yeah, that's right. We went to 53 versus 71. So, okay, you know,
Oh, no, I but,
Yeah.
but why?
Oh, it is on the slide, yeah. The reason why is the reverb blockade radius is smaller, which allows you to pack more pairs into the gate zone without having them crosstalk. Yeah, good question. Okay, so, you know, and to emphasize, this machine only does measurements at the end. So there's not yet mid-circuit readout and feed forward. All right, so performance, I mentioned state-of-the-art fidelities. We have that on this gate-based machine. Single qubit gates that are global, local single qubit gates, you know, both are above 99.9, and then 2 qubit gates are 99.5 as a result of these randomized benchmarking measurements. All right, let's jump into some of these science projects. And I wanted to go through you know, one example of each. You know, there's a lot of different things that you know, we have done and our partners and customers have done. But I really like these two because they demonstrate kind of high impact work. But you know, just to give you an overview for Aquila, there's basically, you know, the way I think about it is four quadrants. You can think of equilibrium and non-equilibrium problems that are classical or quantum. And I will you know, just flash this here and talk about this, you know, non-equilibrium quantum problem, which is kind of one of the hardest, but a good fit for the device. And so, you know, it also emphasizes, like, look, you know, in this early stages, that, you know, problems have to be often matched to the device, or at least co-designed with some device parameters. So this work is about observation of string breaking on a 2+1D Rydberg quantum simulator. So it's a lattice gauge theory that is implemented on the Rydberg Hamiltonian. And this was actually the idea for mapping that onto the Rydberg Hamiltonian came from our collaborators at Innsbruck University, Peter Zoller's group. And the experimental work was done here at QuEra. And by the way, Boris kind of started that project. So when he was at QuEra, and I should have said, Boris also built a lot of the Aquila machine with his own hands. So a lot of what you see is something you can actually go ask Boris about if you're curious after I leave. Good. Okay. So okay, what are lattice gauge theories? What are gauge theories? What are lattice gauge theories? What is string breaking? You know, lattice gauge, gauge theories is something that describes, you know, the standard model, and you know, one of the hardest ones, and the ones people are really interested in the context of nuclear physics, nuclear structure, is the quantum chromodynamics. So how do quarks interact with gluons inside nuclei, and how does that result in atomic structure? You know, there are some fundamental questions that are very hard to compute from the bottom up in these models. And even the experiments which try to, you know, kind of understand this physics, which are typically large colliders, they have trouble interpreting the data because it relies on kind of, you know, understanding what these many particle interactions look like in quantum chromodynamics. And, you know, lattice gauge theory is actually a theory that was developed to simplify the problem a little bit for computations. It's effectively saying I'm going to discretize my, you know, my space into a grid, and I'm going to compute, at least qualitatively, I can start to understand the behavior of the model on a lattice. Still a hard problem, lattice gauge theory, but it does have, it does retain some of the core properties of the, you know, real physical gauge theory that you care about. One of the phenomena in quantum chromodynamics that is fascinating is confinement. So you don't ever observe quarks on their own, and that's because they have this linear potential that if you pull them apart, they get more and more energy until the energy to create another pair becomes lower than the energy in that's what's called a string that binds these quarks together. And so this question of how do these strings form? How do they break and reform in this quark gluon of plasma is a very interesting one. It turns out lattice gauge theories can show this phenomenon. It turns out even on our quantum simulator, we were able to see that phenomenon. Now, very important to say is that it is not yet a solution to quantum chromodynamics. It's not even the correct gauge theory, okay? But it does show this confinement physics and the string breaking physics. And what was very cool is actually, as we were working on this implementation in this analog Rydberg simulator, the Google Quantum AI team were reaching similar results in yet another gauge theory, in a Z2 gauge theory, on a gate-based quantum device. And so I think the nice part of the story is like some of the problems can really be studied both on analog machines and on gate-based machines, and they can access different physics and different levels of control. And in both cases, this was an observation of string breaking. All right, so on the analog device, on Aquila, implementing the lattice gauge theory basically comes down to arranging the atoms in Aquila, remember their programmable positions, into a Kagome lattice, where the sides of the lattice actually represent the lengths of the dual hexagonal lattice, and the lattice gauge theory lives in that hexagonal lattice. And if you try to prepare the ground state of the system with Rydberg excitations, where you make the detuning positive and try to excite as many Rydbergs as possible, subject to the blockade constraint, turns out that this blockade constraint maps onto the Gauss law, into Gauss's law on this lattice, on this hexagonal lattice. And that is a local gauge constraint that you need for a U1 lattice gauge theory. If you take the Rydberg Hamiltonian here, it is written in kind of theory units, dimensionless units. But if you transform it under this blockade constraint and take into account long-range interactions between Rydbergs, this 1 over r to the 6, turns out you'll get this gauge matter interaction term, which is what you need to actually see string breaking. You have a mass term for the particles you would create when strings break. And then you have electric energy that grows linearly with the length of the string on this lattice, which is this confinement phenomenon. So, and the confinement emerges when you basically have blockade constraint in this Rydberg system on a Kagome lattice with long-range interactions. So it's a pretty tailored problem for this particular simulator, but now this quantum simulator can study the physics of it. This is an example of a string in this 2D system, okay? Which actually, if you think about physically, it translates into the pattern of Rydberg excitations on this Kagome lattice. There are actually multiple strings in the 2D system, and that's one of the nice things about the 2D simulator is 1D systems are typically much easier to understand, and 2D starts to get into the realm where classical methods start to fail. I'm not going to claim that this has quantum advantage over the best classical methods, and the quantum simulator is noisy, but it does show some of the physics, as I will explain. If you look at if you try to prepare the ground state of the system subject to the blockade constraint, so in the correct gauge sector, you will find that there's actually a phase boundary between the kind of deconfined and the confined phase. And within the confined phase, and by the way, this is a numerical plot for now. And you will find that there are two kind of phases. There's a phase where you have some superposition of these strings in 2D, and then you have a broken string phase where you've basically created pairs of charges in this lattice gauge theory and broken the string. And you can prepare these states in equilibrium. So you can prepare a broken string state or a string state. And to start with, that's what we did. We just mapped out this phase diagram and prepared at equilibrium effectively what looks like different patterns of Rydberg excitations. So this one represents one of the strings in this part of the phase diagram. This pattern that we actually see on the camera, right, represents a broken string in this part of the diagram. And you can see if you overlay this with this, you kind of see agreement with the numerical results for this equilibrium question. Next thing is to look at the dynamics, and that's also kind of always the hard part with simulating these many-body systems. And what we did here was prepare the ground state in the string, and then suddenly quench the system by increasing the string tension. Actually, it turns out our local degree of freedom that allow us to shift the resonance of individual atoms, allow us to effectively do that, to flash on a higher string tension without necessarily like stretching it. And so what we see is then that string breaking in time. And this data is actually for this 1D short 1D string. And you can see the probability of the, if you don't make the tension high enough, over time, your probability of broken string stays and your probability of the string decays due to decoherence, but more or less, you're not quenching the system here. Here you're starting to quench the system, and you can start to see this, string turn into broken string, and you can see some coherent oscillations in time. And if you actually look at a fixed time and look at the probability of the string and the broken string, you will see a resonance. You'll see that there's a particular string tension at which you have the largest probability to break. And that's a coherent phenomenon in string breaking that in this very simple system was reasonably easy to describe by looking at all these intermediate broken string states. So if you start here and you want to end up here, you kind of have to go, create this pair, or go through this path and then eventually end up in this state. And you can explain the resonance phenomenon as basically saying that, okay, the energy of this state and this state are in resonance, and you can now make a transition. Turns out if you do this naively and just look at the classical energies, you will find that the resonance is at a different place from if you did the experiment or if you did the correct numerics with all of the quantum effects in there. And that has to do with multiple paths here that really bring you from string to the broken string. And this was a very nice, you don't think of it as like we discovered something that is new in string breaking, but we were able to benchmark our numerical methods, for example, that calculate the string breaking by finding agreement with the experimental data, which is beyond what naive classical model gives you. All right, so that was our string breaking demonstration. Oh, please.
Please repeat how you implemented the quenching.
So the way that we did it, and the detailed explanation is a little bit. I didn't give you enough background to explain this, but string tension comes from the fact that if your Rydberg excitation is in a pattern that corresponds to a string, then the next neighbors, if they're in the Rydberg state, will actually contribute to the energy of that pattern, and that will be linear with the length of the pattern. And what we can do is we can, one way to change tension is to change the distance to those next neighbors by like scaling the whole thing. Another way is to locally apply an energy shift to the pattern, to this pattern corresponds to the string, but every other atom, just the atom that has the Rydberg, which is equivalent to having an energy shift from a next neighbor. So it's like a substitute for like very quickly scaling the whole pattern by applying local control. We can discuss more because it's very hard probably to understand this without drawing this stuff. But it was ultimately local control on the string, which we know, right? It wouldn't work, for example, if you had like a superposition of strings. And that's why this experiment we only did on a 1D system, because there's only one string, so you know where to apply your energy shifts. Good question. Anything else about string breaking? Because I'll jump to QEC, and this will be really fast now. Science with Gemini, so our gate-based machine. Now, we haven't done almost anything except for that one project I'm about to talk about, but it is a platform where you can think about developing decoders, QEC codes, resource factories in the QEC sense. You can think about quantum classical hybrid computations, some kind of machine learning workflows in the NISC circuit sense. And as I mentioned, compiler co-design, algorithm hardware co-design, and then developing neutral atom architecture itself. It's something suitable for this low-level API that we're building right now. But before we ship this, so this machine, by the way, I mentioned before, we shipped it to Japan. It's in Japan right now, and it's, you know, we're trying to bring it up. Before we did, though, we did this demonstration of logical magic state distillation. So here's a team that spearheaded this. And of course, this was a very, you know, it was actually a company-wide effort to build that machine and to show that landmark result. Why is this result important? So in water magic states. So what you want to do to build a universal quantum computer is you want to have Clifford gates and you want to have some non-Clifford gates. Turns out that the non-Clifford gates, turns out that you cannot do the whole set transversally, meaning that just bringing a block of logical qubits on top of each other and doing the gate, which is what neutral atom platform is really good at. And so typically the model of the kind of circuit-based model of computation relies on producing these T states non-fault tolerantly, and then filtering down, so losing a lot of them, but, you know, picking the ones that worked and then injecting them into your computation. And that's what's called like a resource factory or T factory. And so up to now, this process called distillation, and up to this work, nobody managed to yet demonstrate T-state distillation on logical qubits. So this was the first demonstration of logical magic state distillation. And this is a critical ingredient towards universal fault-tolerant quantum computing. So we think of it as kind of a core building block of our next generation machine. Let me skip to what we actually did. So now, what are logical qubits? You take a bunch of physical qubits and you encode information on them in a way that you can detect errors and correct errors if they happen locally on individual qubits. And you have ways of measuring that without perturbing the quantum information on the logical qubit. And the two kind of logical qubits that we constructed for this work were Steen codes, 713, for those who are experts, and 1715, which means that, you know, we had two different sizes of codes, which, you know, typically, if you're past threshold, the bigger the code, the better the error correction is, and the lower the error. And that's what you want to show, that, you know, you don't want to build a logical qubit unless it actually helps you. And so we went from, and D is basically kind of the size of the logical qubit, but it also tells you how many errors you could actually detect and correct. So we did a D equals 3 and a D equals 5 code. And what we did was we encoded the magic state into 5 logical code blocks using this code, and then also separately using this code. And then that's the circuit, the physical qubit circuit that does that encoding. Now that's not fault tolerant. All the physical errors will make your logical T state very low fidelity. But now what you can do is you can run this algorithm, which is called this circuit. It's called distillation, and think of it as like a higher level error correcting code that will decide, will kind of bring the good logical state into one of your 5 logical qubits. And then by measuring the other logical qubits as sort of say syndromes, you can decide whether this logical qubit that you want to now send to as an output of your factory to your computation, the bigger computation, you can decide whether that worked or not. If it worked, you send it. If you don't, you throw. If it didn't, you throw it away, and you have to run this process again. So that's how distillation factories work. And so we did this demonstration and showed that we can get, you know, by now detecting syndromes from the base code, from the 713 and the 1715 code, we were able to decide how many of the errors we're willing to tolerate. And if you filter down, if you like start to throw away those instances where your base code showed that there was an error, you can get logical magic state fidelities that are higher than what you injected initially, which means your factory is working. Now, one caveat is, okay, here's post-selection, but of course, if you have mid-circuit readout and feed-forward, these syndromes that you measure in the base code could be used to not just throw away the data, but correct it before you inject it into the computation. Okay, so logical magic states with you know, kind of record fidelity and most importantly higher than what you injected. And And now how does that depend on the code size? And you can see that, okay, this is the trivial case. Code distance 1 is just 1 physical qubit. Code distance 3, you have an improvement in the magic state fidelity. And you can see that now, we're not operating very far below threshold, right? And so your code distance 5 starts to perform worse again. So you win by encoding into the smallest code block you can make. And then if you try to go bigger, your error correction isn't working. And so this just tells us, okay, we need to be further below threshold. We need to have higher physical qubit fidelities for this code. Now, there's other codes that might have other thresholds, and that's another dimension you might explore. And of course, because this is post-selection, the higher the code distance, the more you throw away. So that's the acceptance fraction of your factory. These numbers are not good enough to run a factory for deep logical circuit. But now we're thinking about the next step of how do you get these numbers how do you make this into a real useful magic state factory? I wanted to end with this because this shows you how the processor actually is running that whole circuit. Each row is one of those 1715 logical code blocks. So 17 physical qubits in that row encode 1 logical qubit. And now you have 5 of those. And when you see these qubits being moved, when you see rows being moved to each other, actually what happens when they get moved to each other is you get this entangling gate. And when 2 rows are next to each other, you actually have a logical qubit operation. It's a logical qubit CZ. And when you have columns moving to each other, that's the physical qubit operation that encodes the magic state into the logical code blocks. So we're doing the encoding in parallel by moving all the column operations, and then we're doing the magic state distillation circuit where each row kind of is the natural operation. You don't have to do any complicated operation. It's the one step, right? Like one row moves to the other row, boom, CZ gate on the logical qubits. Yeah.
This is an illustration. It's actually.
Well, these are videos of actual atoms. Of course, because you're imaging it, that's not executing a computation, right? It's just it's showing you the moves that happened underneath. You can't look at them right in the middle. So this shows you the move program that is being executed. And it's also slowed down by a lot. So each of those moves is like 100 microseconds. Right. All right, so we're coming up on the hour. To recap, I explained to you a little bit how our 2 generations of machines, the first and the second generation, work, an analog system and a gate-based system. I showed you some interesting results in quantum simulation and in quantum error correction on these 2 systems. And the last thing I want to say is that while we're pursuing this very aggressive hardware technology roadmap that allows us to operate on larger and larger qubit numbers to implement this error correction under the hood, the theory has been making incredible advances in lowering the resource requirements for first utility scale problems. And there's actually a lot of work at QuEra, at Harvard, globally, and we're trying to incorporate all these algorithmic improvements and architectural ideas into the machines. But this, I think, is one way to think optimistically about the quantum computing, utility scale quantum computing stories. Not only, okay, we're advancing very fast towards bigger and bigger systems, and error correction is starting to work, but actually, we used to think that it requires 10 million qubits to do Shor's algorithm. That's no longer the case. There's, a lot, and quantum chemistry resource requirements for first utility problems have come down. And so we really think that combining all these algorithmic improvements and all the hardware improvements in the next 4 years, we're going to be at a place where first quantum utility can be demonstrated on neutral atom computers, at least. So that is all. Thank you.
All right, time for questions. Yes.
Bit about the T-gate index. So one of the approaches that you're using,